I can't believe you're still watching this. Hopefully, you're getting something out of this. My name is Robert Weiser. This is going to be EOC review number 5. I'll have this document linked into the description of the videos. This is going to have 4 videos, 4 parts. First part's going to be absolute value functions, inequalities, and equations. I'll show you graphically and by hand how to do these. Second part's going to be exponential functions and logarithmic functions, solving equations with logarithms. The third video will cover things like key features of graphs. And the last thing, we'll wrap it up with a little bit of statistics. If you have had time to do statistics in Math 3, there's so many things in there, it's likely you may have not done much. So don't worry too much about statistics. It's not a big chunk of the EOC, but I will go over that in my last video. Stay tuned. Let's do the first one. This is going to be review number 5, part 1, absolute value functions. Here are the standards from the North Carolina Math 3 course of study. I'm going to show you how to isolate absolute value variables by hand. I could walk you through all these, but I'm just going to get right into it. So if you want to pause this and write any of this down, you can. I also have this document linked in the video if you want to print it out. How do I solve an absolute value equation by hand? Well, this equation is going to this video is going to address that. So the first thing is we want to solve that by hand. Anytime that you have an absolute value equation, you want to isolate the absolute value. Start with adding or subtracting the numbers that are outside. 4 plus 3 is 7. So we have 1/2 absolute value, 2x minus 7 is equal to 7. Then your next step is going to be getting rid of anything that's outside. We could divide by 1/2. Since that's 1/2, I'm more likely to multiply by 2 to get rid of that 1/2. But if it's just a number, divide by it. So 7 times 2 is 14. So that's going to clean that up. You have the absolute value of 2x minus 7 is equal to 14. From there, you're going to have 2 equations, all right? One with a negative 14 and one with a positive 14. The first one, you're just going to rewrite it as 2x minus 7 equals 14. You're going to leave everything as is, just take the absolute value bars off. The other one is 2x minus 7 is equal to negative 14. When you solve both of those equations, you'll get both of those answers. Add 7 to both sides. You're going to get 2x equals 21. And then 21 divided by 2 should give you 10.5. So that's one of my answers. The other one is 2x minus 7 equals negative 14. So we're going to start by doing the same processes. Add 7 to both sides. Negative 14 plus 7 is actually going to be negative 7. So 2x is equal to negative 7 in this case. When you divide both sides by 2, you're going to get a negative 3.5. So x is going to be negative 3.5. And both of those solutions work. You can go back and test it into a calculator and check if you need to. You can see from my Desmos plugins for 10.5 and negative 3.5 for the original expression, I do get 4, and that matches the right side of the equation. So both of those are going to be legit solutions. Also, you can graph the equation and get the solutions. And there you go. Both points of intersection are going to give you the same values that we got by hand. So those are your 2 answers. They're both legit. Let's move on to the next question. Now, you may notice that on this document, question number 2 is the same question, but it's an inequality. So instead of an equal sign, it's a greater than. You can treat this like an equation if you'd like. Okay, when you solve that by hand, if you just ignore the inequality because they're confusing, make it an equation. But when you do that, you have to go back and test to see which answers work. So I recommend doing something like a number line test, where if you think about a number line, all right, so I'm going to just draw a number line out, and I'll do my boundaries at negative 3.5, since that's my smaller number, and 10.5. And I made them open circles because of the greater than, okay? I want to test 3 different numbers. I want to test the number over here. So would negative, 5 be a legit value? Or I want to test a number up here, maybe like 12, see if that works. Or maybe a number in between. Let's say I test 0. Okay, either these 2 are going to work on the outside, or the 0 is going to work on the inside, but it's not going to be all 3. So we can go back and we can test our values. So you can see here, if I plug in a -5 into here, I get a 5.5. And 5.5 is actually greater than 4. So that's actually a legitimate answer. If I plug in, let's say 12 in there, I also get 5.5. So 12 works, but the number in the middle, 0, does not work. So the way that my solution set is going to look is you're going to have this, all the numbers that are going to be below -3.5, so less than -3.5, and all the numbers that are going to be above 10.5, but not any of the between numbers. So I'm going to have x is less than -3.5, or since it's going in opposite directions, x is greater than 10.5. And that would be my solution. Now, I want to talk to you about how you can utilize graphs to assist you with that as well. So let me write this down and pause the video. I'm going to get rid of all this. All right, 3 things you want to do. You want to treat this as an equation and do the left side and the right side and find the points of intersection to get those values. Then you also want to graph the entire inequality. You're allowed to do that on here. So you look at that shaded region and you can see it's going in opposite directions. So not opposite directions is going to be an or situation. The dashed line means we're not going to include those points of intersection. So we want open circles, and that's going to coincide with the less thans and the greater thans as opposed to the less than or equal tos and the greater than or equal tos. And so that kind of backs up your answer. All right, let's go to the next question. Well, this does look familiar, doesn't it? It's the same number, same variables. The only difference is that less than symbol. So instead of a greater than, we're going to do a less than. And how that works is when you solve that out, you're going to have the stuff shaded between them. So all the same here, I'm not going to resolve these out, but you're going to have, when you do the equation, x equals, I believe the answers were, oh, I already forgot. Let's go back here. Right, -3.5 and positive 10.5. But if I change that one direction, it's now shaded in between instead of outside. So I'm not going to redo it by hand because I already did that twice. But if I draw this graph out, it's going to look in the in-between shadedness. So picture a number line. And from the graph, you're going to get -3.5. Again, leave those open circles because it doesn't include them. And then 10.5. And everything in between those is going to get shaded. That's your solution set. The way we write that solution set is a little bit different than the ones going apart. Since the x values are all between those, we say -3.5 less than x less than 10.5. And so that would be your solution with the graph and the inequality statement. All right, pause that video, write it down if you need to, and go on to the next question. Well, we just can't seem to avoid this question, can we? It says, what's the smallest integer that x can be to make the inequality in question 3 true? So we have our solution set for question 3. So I left that up here. Now, when I'm talking about the smallest integer to make that true, I want to think about what integers are solutions, okay? So if you think of this number line, and you know that -3 is not, -3.5 is not a solution, but if I go to the next integer, -3, that is. And the next one, -2, and the next one, -1, 0, 1, all the way until we get to 10. But once I hit 10.5, we're no good, right? So all the integers that are solutions are going to be all these numbers. 11 does not count. -4 does not count because it's outside. So my smallest integer that makes this true is going to be which one? That's right, -3. The largest would be 10. So largest and smallest. Remember, an integer is a counting number, anything that's on a number line. So -3 is your answer. Finally, a different type of problem. Company manufactures jeans. The jeans are required to have a waist measuring 85 centimeters. The company will not sell the jeans if they are off by more than 1 centimeter. That's your margin of error. Let X represent the waist measurement of the genes. Which absolute value inequality represents the range of acceptable waist measurements for the genes? Choose only one. So in this problem here, you want to think about how much you can be off by. So let's say I have this weight measurement, waist measurement for rather, I measure the genes, I get some value. Okay, so let's say the genes are, 90 centimeters. Now, how much am I off by if I'm supposed to be 85 centimeters? Well, that difference is going to be 5, right? Let's say my waist is uh 84 centimeters. How much am I off by? Well, if I subtract that, I get -1, but I don't say I'm off by -1, I just say I'm off by 1, right? So you can go either way with your subtractions. So what we do is we call this waist measurement X, and we just subtract our ideal, what we want it to be. So our ideal is going to be, I'll just make a little formula here. And we wrap it in an absolute value because we don't say I'm off by -1, I just say I'm off by 1. So that means that amount that I can be off by can be no more than, or that difference could be no more than the amount I'm allowed to be off by. In this case here, it's going to be 1, but I'm just going to call this the error. It's also called tolerance. Gosh, it's got a couple different names: tolerance, error, wiggle room, whatever you want to kind of call that. So in this problem here, what's my tolerance? How much can I be off by? Well, in this case, it's going to be 1. All right, that's how much I can be off by and still be okay. So when I'm making my inequality, I'm going to say the absolute value of X minus 85 centimeters can be no more than 1 centimeter. That's how I want to set that up. So it's going to be this one right here. You may find it helpful to see this as a graph. So write that down. I'm going to take it off so I can show you on a graph what that looks like. Now, if you put that inequality in, you're not going to get anything. You have to scroll. Think about the number 85. We got to go right 85. So I'll go all the way over here. Now let's look. What this is telling me is anything between 84 and 86, including those numbers, is legit. Now, when you think about a manufacturing process, you might be off by like half an inch or centimeter or, small fractions of that. So there's a lot of variation, but we don't want to be less than 84 or greater than 86. Anything between 84 and 86 is valid. And that's how the inequalities get set up. So always going to be less than, always going to have your ideal inside and your error on the outside. That concludes video number 1, absolute value functions. The next video is going to be covering exponentials and logs. Stay tuned.